Unit 1, Lesson 2, Evaluating Limits Algebraically. So algebraically means that we're going to evaluate these without the use of a calculator in the graph, unless we're going to be able to sketch it ourselves. Now you want to remember that the limit is the intended height of the function. So in part A, if you can substitute in the value you're approaching and get a real number answer, then that's the limit. So the limit as x approaches 0 of e to the x cos x. Well, if we substitute in 0, anything to the 0 power is 1. The cosine of 0 is 1. So 1 times 1 is 1. That means this limit is 1. It's approaching the intended height, the actual height or y value of the function of 1. Let's look at number 2. The limit as x approaches negative 2. If we substitute in negative 2 for x, we get negative 8 to the 2/3 power. Now when we're doing fractional exponents, these are skills that we have to remember from Algebra 2. That's power over root. So we have to do this without the use of a calculator. So I recommend doing the root first because it keeps our numbers smaller. So the denominator is the root. It's a cube root of negative 8, which would be negative 2, and negative 2 squared, well, that's a positive 4. So that's the limit. It's the intended height of the function. We're not always going to get a nice outcome like this. What happens if we get 0 over 0? 0 over 0 is what we call an indeterminate form. And I'm going to talk to you about a few different indeterminate forms that we have to be on the lookout for this year. Now, if you get 0 over 0, it means that the limit isn't necessarily 0. The limit maybe exists, maybe it doesn't. It's indeterminate in this form. So you have to do something in order to evaluate the limit. One option, reduce, rewrite, then evaluate. So let's take a look at number 4. If we were just to plug in 2, this simplifies to 0 over 0. An indeterminate form, you've got to do something. Now we actually did this in lesson 1. We can factor this one. Simple MAM factor on the top. On the bottom, we have a GCF of 2, and when we factor out the 2, we've got difference of perfect squares in here, so we've got to keep going. And once we have this factored completely, we can now cancel common factors. So bye-bye to the x minus 2, and that's it. Now that I've rewritten what we have left, remember we are looking for the intended height of the function. So there's something going on at 2. Maybe there's a bullet hole in the graph, maybe there's a jump or an asymptote, I don't know. But now that I've reduced this, I try re-evaluating it too. Now when I plug in my 2, I get 1/8. That's the limit. That's the intended height. When this happens, when you start off with an indeterminate form and wind up with a real rational answer, then that means you're approaching a hole in the graph. So the limit exists. The intended height is 1/8, although you're going to find a hole in the graph at the value x equals 2. Let's take a look at number 5. The limit as h approaches 0, 3 plus h squared minus 9 over h. I'm hoping that this is sparking a little memory of, oh, I remember this limit, it's something special, but we'll get to that in a couple of lessons. If you're thinking derivative, good for you. Otherwise, right now, we're going to evaluate this as a limit. Let's plug in 0 for h and see what happens. Uh-oh, plugging in 0. I wind up with 0 over 0, an indeterminate form. Now, I can try and factor this one. If you look at the numerator here, this is actually a difference of perfect squares. But another option is to expand this out. Let's multiply 3 plus h squared and expand it out. Bottom line, we got to try something. 3 plus h squared means 3 plus h times 3 plus h. And here we go. We're going to have to FOIL this out. Once it's expanded, now for the fun part, start reducing. And you'll notice that we can factor out an h now in the numerator. Again, we get to reduce. And now what happens when I plug in 0? Well, now I'm going to get 6 plus 0, which is 6. So the solution is 6. That's the intended height of the function. It's okay that we started off with 0 over 0. The limit can still exist. Let's take a look at number 6. First thing you always try is try evaluating at 0, because like in number 1 and 2, if you wind up with the real number answer, you've got nothing else to do. Not so lucky. We wind up with 0 over 0. That's the clue that we've got to do something else. This is an indeterminate form. You might be noticing I'm trying to choose examples that hit upon all your different algebra skills. This year, your algebra skills need to be on point. You are expected to know, remember, and be able to execute all of the skills that you've learned up until taking this AP calculus class. What we're looking at here is a complex fraction. So there's a couple of ways that you can reduce a complex fraction. I'm going to kind of use the most universal one, meaning it works in all complex fractions. Look at all these mini denominators here and come up with the least common denominator. In this one, the least common denominator is both the 8 and the 8 plus x. So I went ahead and multiplied it to all three parts of this complex fraction, so now I can start reducing the pieces that can cancel out. Let's rewrite what we have left. Tricky part about this one is the silly mistake in here. Look at the numerator. When this cancels out, this is minus 1. That then is going to be multiplied, look down here, to the 8 plus x. Well, that has to be distributed. We have to distribute that negative sign. All right, fun part. 8 minus 8 cancels out. Now I've got this negative x on the top here and a positive x on the bottom, so those guys could cancel out, but I'm going to need my placeholder of negative 1 in the numerator. Now that I've fully simplified, let's plug in 0. Notice that at the end, I'm always going back to evaluating at the x value that we're approaching, because in the end, I'm looking for the intended y value of the function. So we've got negative 1 over 8 times 8 plus 0, or a final answer of, let's see if I could squeeze it in here, negative 1 over 64. So again, I do have a value for the limit, even though I started off with an indeterminate form. Now, it is possible to go through all the work and find out that the limit is actually approaching 0. It's also possible to go through all the work and find out that, hey, we're never getting rid of the 0 in the denominator. A 0 in the denominator, when then there's a real number in the numerator, that's when you can settle on that the limit doesn't exist. All right, let's look at this guy. The limit as x approaches 0. If I plug in 0, there it is. I wind up with indeterminate form. So what do I do now? I can't factor this. It's not a complex fraction. There's nothing to expand out to turn into a polynomial. This is where we're going to need the conjugate. The conjugate is going to be the same radical expression that we have in the top, except I'm going to change the sign in between to plus. So in order not to change the value of the function, I have to multiply the conjugate into the numerator and the denominator. Now, what's so special about the conjugate is, yes, when we multiply this out, we do have to FOIL. First, outside, inside, last. But conjugates, you'll notice that the outside and the inside are identical expressions, just with opposite signs. So they always cancel each other out. So even though I'm technically foiling first, outside, inside, last, if I use or multiply conjugates, the outside and insides always cancel. So I'm really just multiplying the first and the last. Another quick reminder is that when you're multiplying radicals, radical times a radical, you wind up with just what's left underneath. So the radicand 3 plus x comes out of the radical when I multiply square root of 3 plus x times square root of 3 plus x. I'm not going to write the outside and inside and cancel them. It's a waste of time. That's why I chose the conjugate. So I'm going to jump right to positive times a negative is a negative. 3 comes out of the radical. And instead of distributing the bottom, I'm going to leave this as 2 terms, because in order to cancel, I'm going to need to see the 2 different factors in the denominator. I've got these nice like terms to cancel in the numerator, the positive and negative 3. And then that leaves now this x and the x that I left out in front. Those are now free to cancel. Remember, you can't cancel through addition and subtraction, but you can cancel through multiplication. Notice I snuck in that 1 as the placeholder. So I'm rewriting what I have left. In the end, how do I evaluate the limit? I plug in the 0. So I've got 1 over the square root of 3 plus 0 plus square root of 3. Combine like radicals, 1 over 2 square root of 3 is the value of our limit. All right, so here's something lovely about the AP exam. On a free response question, like we just did, where you're showing all your work, you don't have to simplify anything. So this is a perfectly acceptable answer for a free response question. However, multiple choice questions, they are going to make you simplify beyond anything that you've ever even thought you wanted to simplify. But this one, pretty common thing to have to get rid of is the radical in the denominator. You can't have a radical in the denominator, you have to rationalize it. And in order to rationalize the denominator, we're going to multiply both the numerator and denominator by rad 3. So we've got rad 3 over 2 times, again, a square root times itself, just leaves us with the radicands. So we've got square root of 3 over 6. This is our fully rationalized answer. Square root of 3 over 6 is what you would see if this was multiple choice question without a doubt. However, you could have left this 1 over 2 rad 3 for free response. You actually could have left it like this and not even combined the like radicals. But you do have to substitute in the x is 0 because that's conceptual. Once you get to the point where it's just simplifying, that's when you're allowed to stop on a free response question. Part D says utilizing tables, graphs, and domain. There's always going to be certain functions that kind of behave weird and just don't really fit into any of the categories. The first one here in number 8, the function y equals absolute value of x over x, is a common one. Right now you might feel like you're not sure what to do with it, but this is something that I want you to get familiar with. Absolute value of x over x. Take a second, and even though I said we weren't going to use the graphing calculator, plug this into the calculator and see what it looks like. This function has a jump discontinuity. It's a step function. Well, that's because of this pesky absolute value. Absolute value is really secretly a piecewise function. It's equal to negative x over x as long as x is less than 0, or the opposite of x over x, and then it's equal to x over x as long as x is greater than 0. Now, since our function is being divided by x is in the denominator, neither one of these domains can include 0. And that's why you're seeing this step here. It's positive 1, x over x reduces to positive 1 for everything greater than 0, and it's negative 1. Negative x over x reduces to negative 1 for everything to the left or less than 0. So direction plays a huge role in this. In the first part, A, it just wants the limit as x approaches 0. That's a two-sided limit then. I am approaching two different values from the left and the right, so this limit does not exist. It's 0. But if I put a direction, in part B, this is asking me from the right. So from the right, that's coming in just from this side, coming in from the right. This is approaching 1. Remember, it is okay to approach an open dot as long as the road is leading there, and this one is specifically one-sided. Same thing with part C. 0 from the left, that's down here on the graph. As I approach 0 from the left, my intended height is supposed to be at negative 1, and it doesn't really matter that there's a closed dot there. So the limit from the left and the right are not equal, and that goes back to why part A here did not exist. Number 9 is a tricky question. We're looking for the limit as x approaches negative 3 from the right of this radical function. Now, the from the right here is my little red flag that maybe there's more than meets the eye to this one. However, just like I was saying before, we should always really just plug in what we're approaching. So if I plug in negative 3, I wind up with the square of 9 minus 9. Square root of 0 is 0. Which is a real number. This is not 0 over 0. As it will turn out, from the right, it is 0. But I would have a very different story if this limit was from the left. this very same limit from the left, you might start it the same way, but the solution is not 0. Now, how would I be even on guard that this is an issue? You always want to be on the lookout for functions that have a domain restriction. So fractions can't have 0 in the denominator, like our 0 over 0 we've been working with. But radicals, you can't have a negative underneath a square root. Now, this particular function, the square root of 9 minus x squared, is one that we're actually going to come to recognize. And you might already have an idea, those of you that have strong geometry skills. The function y equals the square root of r squared minus x squared. Well, this is actually a semicircle. If you remember from geometry, x squared plus y squared equals radius squared. This is a semicircle since it's a function with a radius of r. There is a restricted domain and it is the radius. So if I were to sketch this semicircle, since we've got 9 minus x squared, the radius is 3. This is bounded between negative 3 and positive 3. You could even solve for the domain algebraically if you wanted by taking what was under the radical, 9 minus x squared, and setting up a quadratic inequality. This has got to be greater than or equal to 0. And you can solve the quadratic inequality to see that the domain of this function is between negative 3 and positive 3. Notice I'm using the square brackets because these are inclusive. It is actually defined at those points. The square root of 0 is 0. The problem with the limit is the direction. The limit as we approach negative 3 from the right, we're on the road. We're on the semicircle, it's going to 0. But as we approach from the left, which I snuck in here, there's no road. The limit is the journey, it's the intended height. So since there is no road to jump on, the limit from the left does not exist. So similarly, the limit as x approaches negative 3, no direction, also does not exist because the limit from the right is not equal to the limit from the left. From the right it's 0, from the left it does not exist. So the limit at negative 3 does not exist. Party, trigonometric limits. I call this the blob. Now before we get to this rectangle of important trig limits that I want you to just really memorize and recognize, I want to start by looking at one important limit. Consider the function f of x equals sine x over x at the x value where x equals 0. Now if I set this up as a limit, the limit as x approaches 0 of sine x over x. The sine of 0 is 0. So this is an indeterminate form. 0 over 0 means you have to do something else. It's indeterminate. But there's nothing to factor. There's no radical to multiply by a conjugate. There is no expanding. There's no complex fraction. So what do? Well, this would have to be one that we take a look at, either making a table of values or taking a look at the graph. Plug sine x over x into your calculator and make sure you're in radian mode. At first glance, we look like we have a nice smooth line here, but again, we're smarter than our calculator and we know that this cannot exist at 0. We can't have 0 in the denominator. So we've got a hole in the graph. So the limit as I approach 0 from the left and from the right, if you use your trace button or if you take a look at the table of values, this intended height is going to 1. This limit is our go-to limit that's going to help us evaluate many trigonometric limits that give us an indeterminate form. Let's take a look at our box up here now. The limit as x approaches 0, now it doesn't just have to be sine x over x. There could be any constant multiple that is matching inside the sine function and also in the denominator. That still goes to 1. And look at this, so does its reciprocal. It also goes to 1. The reciprocal of 1 is 1. Same is true for tangent. Tan of any multiple times x divided by that same multiple of x goes to 1. even its reciprocal. Now, cosine's a little different. Cos x over x doesn't follow this same pattern because cosine of 0 is 1. So I want to separate this table a little bit because the limit that you would want to have memorized involving cosine is 1 minus cos x over x, or 1 minus cosine of any multiple of x divided by that same multiple of x goes to 0. Now this isn't true for reciprocal because the reciprocal of 0 is undefined, but it's true for the negation of this, meaning it doesn't matter the order that we subtract on the top, but this one goes to 0, whereas sine and tangent, those go to 1. So here's what I mean about using this sine x over x as the blob. Let's look at example 10. The limit as x approaches 0 of sine x over 7x. Well, sine x over x, that goes to 1. So that 7 in the denominator is left behind, and this limit is going to 1/7. Let's look at number 11. The limit as x goes to 0 of sine 3x over x. Now, little problem with this one. If there's a multiple in here, let's go back up to our rule. If there's a multiple in here, we have to have the matching multiple on the bottom. So on this one, I would have to multiply a 3 into the bottom in order to get the rule. But if I multiply 3 to the bottom, well, I have to multiply 3 to the top of the fraction not to lose its value. Now this sine 3x over 3x goes to 1, and then 3 times 1 is 3. So if you can blob out or find that sine x over x or sine 3x over 3x, that whole limit just goes to 1 and you're left with the constants. As you get better at these, you're actually going to be able to tell that without doing all this math. I'm going to erase number 11. See how you look at this and you see the 3 as a multiple? Well, then 3 is the limit. It's because of the work that I just showed you, but these you often don't have to show all of that extra work. Now, just like with sine x over x, you can blob out tan x over x. It also goes to 1. So number 12 says the limit as x approaches 0 of cos x times tan x over x. Well, this tan x over x goes to 1. So I can now plug in 0 into cosine, and the cosine of 0 is 1, so 1 times 1 is 1. You can't forget your algebra though. In number 12, I was allowed to blob out tan x over x because that was multiplication in the top. Look at number 13. The limit as x goes to 0 of 3 minus 3 cos x. Well, I can't blob anything through subtraction, but I do notice I have a greatest common factor there. Let's factor out the 3. Now that I've factored out the 3, I can blob out 1 minus cos x over x, but ooh, that one goes to 0. Anything times 0 is 0. Number 14, the limit as x goes to 0 of 2x plus sine x over x. Again, we've got to be careful about algebra. I cannot just blob out this sine x over x because you cannot group this through addition, just like you can't cancel through addition. So I have to split this up. Since we're dividing both terms by x, it's dividing the sine x and the 2x. Now I've sort of legally separated these two terms. This first fraction, if I just plug in 0, I'm going to get 0 over 0. Well, that's because this can reduce. I can cancel out the x's. And sine x over x, that's a blob. That goes to 1. So this limit actually goes to 2 plus 1, and I get 3. Now, in all honesty, I was a little bit lazy on number 14 there. I really should always start a limit by plugging in the 0. You could double check. This was 0 over 0, so it's an indeterminate form. But look at number 15 now. First of all, this just looks a lot more difficult, but I also have x approaching pi over 4. So first thing I should do is just check, what is this at pi over 4? All right, here's another big deal. You have to be able to evaluate the trig values of all of your reference angles. Being able to see pi over 4 as 45 degrees and knowing sine, cosine, and tangent of 45 degrees. Now, you can use your special right triangles. So if you remember your isosceles right triangle, the 45, 45, 90 right triangle, 1, 1, rad 2, you can use this to help you remember your values. Tangent of pi over 4 is 1. Sine and cosine are both rad 2 over 2, or 1 over rad 2. So, oh boy, this winds up being indeterminate form. When I'm going to be having you work on problems on your own, honestly, this is what I put in there. You need to get super comfortable with evaluating trig functions without the use of a calculator, and this is going to be what you're practicing, not so much the limit involving trig functions, but being able to just evaluate these values of all your reference angles. But after all that, this is an indeterminate form. I have to be able to do something to figure out if this limit exists or not. Now, doesn't factor, it's not a conjugate, but I can rewrite tangent in terms of sine and cosine. I got to do something, that's what I'm going to try. Now that I rewrote tangent as sine over cosine, now I've made a complex fraction. So I need to simplify my complex fraction. Common denominator, cos x. So I need to go through and multiply all three pieces by cos x. This reduces. Let's rewrite nicely what we have. Well, when I rewrite this problem, look at what happens. This is actually really nice. I have sine minus cos x on the top and the bottom. So this problem was seeming pretty terrible, and all of a sudden now it simplifies to 1 over cos x. Now what do? Plug in pi over 4. We're looking for the intended height of the function. So 1 over the cosine of pi over 4, or in other words, the cosine of pi over 4, and I get a final answer of rad 2. Unit number 16. The limit as x goes to 0 of x plus 3x squared over sine x. Just plug in 0 and we get 0 over 0. So this is kind of a mixed bag. What I see on the top here is I could factor out an x. And by doing that, look at what I've got. I can blob out. It's the reciprocal, but I see my sine x over x. In this case, it's x over sine x. What does that go to? 1. So plug in 0 for x. And we get 1 plus 3 times 0. Or a final answer of 1. Last one, number 17. This looks crazy. The limit as x approaches 0 of sine 2x over sine 5x. If we just plug in 0, we get 0 over 0. But I want to simplify this right off the bat. See the constants? That's the limit. Now, what actually happens is you need to kind of build these blobs with your algebra. We need to turn this into sine 2x over 2x. We need to turn this into sine 5x over 5x. And it's going to wind up just being the constant. So whenever you see a combination of sines, tangents, or a mix of sine and tangent, just pull their coefficients. So I wrote that down kind of like another rule box. The limit as x goes to 0 of sine mx over sine nx would just be the coefficient m over n. Same thing with limit as x goes to 0 of tan mx over tan nx, m over n, or any combination of sine and tangent together. You're just pulling those coefficients out. So again, you can do this algebraically by creating those blobs, but sometimes you're just wasting your time putting that extra work in when you can kind of just train yourself to say, oh, just pull the coefficients. Number 17, hey, that's just 2/5. Nice job.